We present a unified framework for solving PDEs on manifolds with interior boundary conditions. Such problems are ubiquitous in geometry processing, for example, when using diffusion curves to color a surface or computing geodesic distance to a curve. Our method handles general manifold representations by only requiring closest point queries to the manifold. Many manifold representations exist, for example, parameterizations, meshes, point clouds, level sets, and many more. Each representation requires different discretizations to solve PDEs and enforce interior boundary conditions. We use the closest point method to solve manifold PDEs. This method only requires closest points, shown here in blue, for points in the surrounding space. Therefore, it provides a unified framework for manifold PDEs on a multitude of manifold representations. The closest point method can be applied on complex geometries that can be closed or open, and orientable or non-orientable. Given some manifold S and a PDE you would like to solve, the problem is extended to the surrounding embedding space. An embedding PDE is constructed on this Cartesian space, whose solution agrees with the manifold PDE when restricted to the manifold. Manifold functions U hat are extended onto the Cartesian embedding space to be constant in the normal direction of the manifold, giving U. A grid near the manifold is used to solve the embedding PDE using standard Cartesian numerical methods. Specifically, interpolation and finite differences are used in this work. Prior work on the closest point method can only apply boundary conditions on the exterior boundary. We extend the closest point method to enforce boundary conditions at interior regions on the manifold, which are necessary for many geometry processing applications. Consider a 1D curve embedded in 2D with an interior boundary point shown here in white. Boundary conditions require modifications to stencils near the boundary, but the necessary modifications differ on each side of the boundary. Therefore, the grid is duplicated near the white point to introduce new degrees of freedom, shown as the thick black grid. The grids are partitioned based on the location of their closest points by the normal manifold S_perp, shown in green. The two sides of the duplicated degrees of freedom are colored yellow and purple. Finally, each side of the new interior boundary grid is joined to the opposite side of the original grid. We warp into 3D to show the final grid connectivity. In actuality, the final grid is a non-manifold grid in 2D. The yellow and purple portions of the non-manifold grid are used to enforce interior boundary conditions with techniques for exterior boundary conditions. Unfortunately, constructing the non-manifold grid only works if a global partitioning can be obtained. For non-orientable surfaces, where the interior boundary fully loops around, no global partition is possible. Instead, we locally check each stencil for grid points whose closest points cross the green normal manifold. This example shows an interpolation stencil in orange and a finite difference stencil in red that intersect the normal manifold. Modifications are performed to enforce the boundary condition at grid points whose closest points cross. To successfully apply our approach, we must be able to determine if the closest points are on opposite sides of the normal manifold S_perp. Consider 2 points x1 and x2 with corresponding closest points CPS. A naive approach would construct an explicit representation of S_perp, for example as a mesh, and then check if the line segment between the closest points intersects S_perp. Instead, we compute the closest points to the boundary curve C. The orange vectors will point in opposite directions if CPS of x1 and x2 are on opposite sides of S_perp. Expected convergence rates are verified numerically on a multitude of analytical problems. We apply our approach to applications in geometry processing. In this example, we color the surface of the Nefertiti bust using the Laplace-Beltrami equation with diffusion curves as interior boundary conditions. The heat method is used to compute geodesic distance to interior boundaries shown in black. Our closest point method approach provides a single implementation for multiple manifold representations, which previously required a new implementation for each type. In this example, we design a vector field on the surface of a Mobius strip using a sparse set of directions. Zero Neumann conditions can be used to block direction changes in the vector field. This example involves computing a harmonic map between two surfaces S1 and S2. The mapping is used to transfer a texture from S1 to S2 while enforcing that landmark curves match using Dirichlet conditions. A final example creates a texture on this fish by solving a reaction diffusion equation. Dirichlet and zero Neumann interior boundary conditions are used to control the texture near boundary curves. The closest point method offers an exciting, unified framework for manifold PDEs on black box closest point manifolds, which we have extended with interior boundary conditions. We hope that you will join us in exploring the closest point method for your own applications in geometry processing and beyond.